we are going to find some functions to make this correct. So let's look at the left hand side. We have the second derivative right here, right? And remember, to get the second derivative, we have to differentiate the first derivative. And let me write this down right here for you guys. We have to differentiate, so I put on d dx, that means to take the derivative of the first derivative, which is just dy dx. We differentiate the first derivative, that's how we can get the second derivative. And you see, this notation, we have the d and d twice. That's how we get the d2, like that. Dx twice, so we have the dx2, like that. That's how they come up with the d2y dx2 for the second derivative notation. All right, and on the right-hand side, let me just write it down as how it is. dy dx and square. And now you see, we have the dy dx match, right? And right here, I would like to do a substitution. Let me just call this right here, the same thing right here, to be another variable. Let me just keep track with, let's say, z, okay? So I want to say that z is equal to dy dx. And with this being done, you will see on the left-hand side, we are just differentiating. This is just z. And you can just think about z is a function, and in fact, it's also a function in terms of x. But then you see that dy dx is the derivative. However, the derivative is actually a function as well, right? Anyways, we have d dx z, and on the right-hand side, this is just z squared. On the left-hand side, we can put this down as dz dx, and this is equal to z to the second power. And once you look at this equation this way, this is in fact a separable differential equation, and this is how you do it. You are going to put all the z's together on one side, all the x together on the other side. I would suggest you guys to take care of the dx in the denominator first, so we can do so by multiply both sides by dx. And you will see we have the z squared with the dx. The z is not invited in the x world, so let's divide both sides by the z squared, so they cancel. Bring that to the other side, I'll put this down as 1 over z squared. Okay, 1 over z squared is the same as saying z to the negative 2, and we have the dz like this. And on the right hand side, we have the dx. And now, the deal is we can just integrate. And let's do that right here and right here. So, the integral of z to the negative 2 power, let me just add 1 to the power, we get negative 1. And we divide it by this new exponent, we will have 1 over negative 1, like that, right? So you see this is just going to be negative, and we have z to the negative 1 power. And as I said, I want to show you guys all the steps. This is the integral. When we integrate something, we should add a constant, and I will add a constant, so let me put on plus c. However, you know, on the other side, we also have another integral. I will also have another constant. Therefore, let me call this constant to be c1. On the right hand side, when I integrate, this is technically 1. The integral of 1 in the x world is just x. And then I also need to add another constant. Let me just put down plus c2. Okay? Next, I would like to just minus c1 on both sides, so that this and that will cancel. And here is the fun part, and let me just put this down right here for you guys. On the left hand side, we have negative, and we have the z to the negative 1 power. That's the same as 1 over z, right? And on the right hand side, we have x. Here we have c2 minus c1. And you know, c2 is a constant, c1 is also a constant. A constant minus another constant is just going to be another constant. Therefore, I can just say these two together is another constant. I will label that with c3. You see, this is how we keep track with the constant calculations. So let me just put this down as x plus c3. And later on, when you have this kind of things, you can just go ahead and integrate, and you start to keep track with your constant on the right hand side only. You don't need to worry about the plus c on the left hand side, because this kind of things will always happen anyways. You can just go from here to here and say this is c1, and you continue to do whatever you have to do later on. Alright, next, we have the negative right here. So let's go ahead, multiply everything by -1. And then this way we can just get positive 1 over z. And this is equal to -x. And here's another fun part. -1 times c3 is -c3. However, c3 is a constant. -c3 is also a constant. Allow me to just put this down as plus another constant, c4. Okay? So, once again, let me write this down. -c3, I'm just going to say this is another constant, c4. Next, I want to get z by itself. This is 1 over z, right? So I just have to do the reciprocal, the upside down, right? So I will do that. We will have z right here, and this is by itself. And this is technically -x plus c4 over 1, and just do the reciprocal. We will have 1 over -x plus c4. And then we are done in terms of solving for the z, right? And this is it. Well, we are not done yet because we don't just want to solve for z, we wanted to solve for y, right? And the connection between y and z is equal to dy dx. So now we just have to write z as dy dx and then solve for the y from there. And I will do this in blue for you guys because I want to show you this right here. It was the first part. And now I will write z as dy dx, and this is equal to this, which is 1 over -x plus c4. We have to solve the second part, which is another differential equation. But this is not bad. We can just go ahead and multiply dx on both sides. And you see, x and dx are together, and this is dy, and there's no other y's, so we are good. You will see this is just dy, and that's equal to 1 over -x plus c4 dx. You can just go ahead and integrate. We run into the same situation like this earlier. This time I will just show you. Let's integrate 1 in the y world. We will just have y, and don't worry about the plus c, okay? Seriously, don't, because this kind of things will always happen anyways. Just write down y, and we'll just say this is equal, and we'll focus on the integration right here, and then put down another constant on the right hand side only. Alright, integral of 1 over -x plus c4. This is just a linear term, right? So we know we will get ln absolute value of this, -x plus c4. However, the derivative of -x plus c4 is -1. Therefore, we have to divide this by -1. It's the same as just saying negative that. So this is the integral of that. And as I said earlier, we have to add another constant. Here we use the c4 already, so I will add c5. And this c4 was in ln. This c5 is just right here, right outside of the ln. I cannot combine them anymore. And you see, this is the y right here. And in this case, we end up with two different constants. It was because originally we are dealing with a second order because we're the second derivative right here. This is a second order differential equation. At the end, you can expect to have two different constants. And this is it. We have y is equal to -ln of absolute value of this, and then plus c5. And if you would like, you can of course box this for the answer. However, because we are done with the process, we can legitimately relabel this as the legitimate C1 and the legitimate C2 that we want to present for the answer. So now real quick, I'll show you guys that the second derivative of this function is indeed the same as the square of its first derivative. Let's go ahead and differentiate this, right? We will first have the dy dx, and let me maintain the negative right here first. And before I differentiate the ln of this, let me make a remark. Earlier, I kept the absolute value because I did not have any initial value. So I couldn't solve for C1 nor C2. And right here, when you want to differentiate ln of an absolute value, you can just kind of forget about the absolute value. I will make another video explain that in detail. But right here, when I differentiate ln of something, I will have 1 over just this, okay? -x plus C1. And don't forget the chain rule. Look at the inside. the derivative of negative x plus c1 is negative 1. So multiply by negative 1. And the derivative of c2 is a constant, so we will have 0. And this is pretty much it. Of course, we have negative, negative, we get positive, and we will have just 1 over negative x plus c1. And this right here is it. But then I want to differentiate this again so I can get the second derivative. Let me look at this as parentheses negative x plus c1 raised to the negative 1 power. So when I do that, I can get d2y dx2 for the second derivative, and I will just have to take the power to the front, and we'll have negative 1 times. The inside stays the same, right? Negative x plus c1. And don't forget to minus 1 to the power, so we have negative 2. And once again, the chain rule says we have to multiply by the derivative inside. We will once again have to multiply by negative 1. So this is the second derivative, and all in all, you can multiply this, we get positive 1. Bring that down to the denominator, you have negative x plus c1, parentheses, square. This is the second derivative. And the punchline is, we can look at this as 1 over negative x plus c1. And we can put a square on the outside like this. Because now, the inside here is nothing but just the first derivative, right? So I can write this as dy dx inside, and then we will square this. So you see, if this is the function, then its second derivative is exactly the same as its first derivative, and you square that. How cool is this? And let me make a remark. Of course, if you want to have the second derivative to be the same as the first derivative square, another answer for that is all the constant functions. However, constant functions are boring. This is way cooler, isn't it?